Hello, hello. Good to see you. It's time for lecture 14, or if your video is reversed, it's time for lecture 14. Yes, pretty cool stuff, right? I'm psyched. I hope you're psyched too. Let me talk to you about this a little bit. In the previous lecture 13, we talked about light, right? And how there was this discussion about whether or not light is a stream of particles or light is a wave of energy. And people went through and eventually by Einstein's time realized that light was both a wave and a particle. In the study guide for lecture 13, you watched additional videos that sort of explain the concepts. What happens when you think of light as a beam of particles, basically rays, and you can actually trace rays and so forth and figure out how to do things like magnifying glasses or mirrors and things like that, right? Or if it's a wave, and what the result is, if you treat it as a wave, you can see different colors. You can wind up thinking about how they wind up interfering with one another, how they transfer energy. And we can learn about our world and the universe by thinking of light as waves, right? So it's pretty cool. We're going to take that to the next level in this particular lecture, because in lecture 14, our purpose is basically saying, okay, what is light? We now know that light is both a particle and a wave. The particle, it's a kind of particle called a photon, which is a boson, right? Which carries the electromagnetic force. But as a beam, it's got energy that it can carry and can do its own thing. That's what waves do. And think of particles. They each have their own energy because they're moving, right? They have their own momentum. So it's kind of cool. Let's figure out the mathematical relationships for all these different things. And from that, right, remember, don't think of the math as some sort of an obstacle. Just think of it as a way of understanding how things work, like in this instance, light, in a different language. Maybe in a more useful language. I mean, think about it this way. Let's say you're trying to understand the French culture. Let's say you're studying French history or something, right? You can read all the books and so forth in French or in English. Now, if you can't read French because maybe you haven't practiced it or trained in it or you haven't lived in France or whatnot, then what happens is you read it in its original English, which is not original, but you read it in a good translation, and you get a pretty good idea, right? In fact, you can study French history pretty darn well without actually speaking French. But what if you really wanted to get into the guts of it and you're trying to do some, detailed work on understanding the French psyche in the 1780s, or think about what like Napoleon had an influence on France, or Victor Hugo's Les Miserables and all these other, things like 19th century French novels. You want to read those in the French, right? And then you get an understanding of how the universe of France works better. So think of math as sort of like a language in which the universe is written so that it can understand it more effectively, more concisely and conveniently. Not that it's a hard, scary thing, but rather that it's just another language. And you might not be as good at it as somebody else is, but that's okay. That's all right. Bottom line is, don't be afraid of it. Use it. And when you're describing concepts using math, don't think of it as like, oh my gosh, that's something else. Just think of it as like you're translating a foreign language. Okay. And if you get it even a little bit, that counts. It's good. You don't have to be a fluent French speaker to be able to, say, visit France and enjoy the museums and the restaurants and stuff, right? That's kind of what we're doing with physics in this class. Okay, so here we go. We have a few equations. We have a lot of concepts to go about light as both a wave and a particle, and specifically that concept of it being a radiation, right? Electromagnetic wave that radiates out. These days, when we think about radiation, sometimes think about, oh, it's the stuff from nuclear power plants or something like that, or atomic bombs or whatnot. Radiation, in a very general sense, is just all kinds of electromagnetic waves that come from things. And originally, we were saying last time, remember, they're coming from things that are hot, right? So we're going to get to that point about thermal radiation, and from thermal radiation go even further. And now we have this okay. All right, let's just get right into it. Before I talk even more about it, I'm just going to demonstrate some stuff and just show stuff. Remember that the first thing that we did mathematically in the previous lecture, right, was that we showed that in the textbook, right, the definition of the wave, the velocity of a wave, v equals f lambda. The frequency of the wave, times the wavelength of the wave. So let's say, for example, the frequency of the wave, you're watching the wave go by and it's going by 10 waves per second, okay? 10 peaks per second or 10 troughs per second. And then let's say the wavelength, say you're talking about is, say, an inch, right? Then that means that you're getting a speed of 10 inches per second, 10 times 1, right? If it were 2 inches, it'd be 10 times 2 or 20 inches per second. Or you can use meters per second, or you can use, anything that you want to do in terms of the speed and the waves with the lengths and the frequency. The frequency tends to be per second, also known as a hertz. So when you hear something like 101.1 as a radio station on the FM dial, that means that it's 101.1 million hertz or megahertz. So the waves that are coming through and carrying the signal that is going to our ears when we're listening to the radio station at 101.1 FM or something like that, then that means that those waves are zipping by us at 101.1 million waves per second. Wow, that's a lot. So the wave speed of a light beam, or a electromagnetic wave of any kind, right? Speed of light in vacuum, that was measured very carefully over many, many, many years. Astronomers first tried to measure it. Galileo first tried to measure it in the 1600s and was unsuccessful. It was so fast. All he could say was that light was so fast that he couldn't figure out how fast it was. Later on, some folks tried to measure it using astronomical phenomena, did a pretty good job, realized that it was really, really fast. A beam of light could go around the Earth several times in a second. And eventually, they worked at it really hard. And about 1900 or so, around 100-ish years ago, they figured out that the speed was about 300 million meters per second, or 186,000 miles per second. 186,000 miles per second. Wow. Anyway, in the metric system, it's listed at 299,792,458 meters per second. That seems like an awfully specific number, doesn't it? It sounds kind of suspicious. Well, it turns out that it's not that suspicious. I'll tell you all about it in a moment. I just want to finish this thought. Notice how close it is to 300 million, right? In fact, it's less than 1%. It's actually less than 1/10 of 1% off from 300 million meters per second. So in our calculations, anytime we talk about the speed of light, usually we just say 3 times 10 to the 8 or 300 million meters per second, right? We can also say 186,282.397 something miles per second. It means it can go around the Earth 7 times around the equator in 1 second with plenty of room to spare, right? Easily. Wow, that's pretty amazing. Speed of light is very, very fast. Yes, it most certainly is. So if you think about it that way, let me just give you that 30 seconds as to why the speed of light is so precisely 299,792,458 meters per second. Turned out that we were defining the meter way back during the French Revolution. The French Academy of Sciences, which at that time, in the late 1700s, was generally considered to be the most advanced scientists in the world. There were plenty of scientists doing lots of cool things everywhere, but the real core of high quality science was primarily being done in France. So they were trying to create the metric system, and they said, well, let's make the length of a meter to be exactly 1/10,000th the distance between the North Pole and the equator. Okay, that's a long time ago. They tried to do this a couple hundred years ago, and they came pretty close. Turned out that meters is about 3 feet, 3 inches or thereabouts. And as they measured closer and closer, they realized, you know what? The Earth isn't exactly round, and the Earth's distance from the North Pole to the equator can vary depending on how you make the measurement. So they chose a different way to measure the meter that came really close to 1/40,000th, the way 1/10,000, excuse me, the distance from the North Pole to the equator along the surface of the Earth. But said, they kept trying different ways, and they got better and better and more precise, and figured out something. And then they figured out just about 10 or 20 years ago or so, astronomers figured out, and physicists figured out, and chemists figured out, and they all worked together and they agreed, you know what? The most accurate way we can define the meter is no longer about Earth and no longer about atoms and molecules, but about the speed of light itself. The speed of light in vacuum is so carefully and precisely measured now that let's just base the meter on that speed and just define it. Up to that point, it was really close to that number, but not exactly that number because using a different definition. So, well, let's just adjust the meter and make it exactly that, and we'll base it on the speed of light. That changes the previous values by less than 1 part in 100 million or something like that. And it gives us a nice round exact number to work with. So that's why it is 299,792,458 meters per second, which is close enough to 300 million meters per second. And that's what we're going to use. Okay, so if we take that original equation, V equals F lambda, and then we put the speed of light into the V sub W instead, you get this equation, right? C equals F lambda. So the speed of light in vacuum, 3 times 10 to the 8 meters per second, equals the frequency of your wave times the wavelength of your wave, right, in meters. So in that previous example, 101.101.1, right, that radio station, it's the frequency is 101.1 times 10 to the 6, so 101,100,000 hertz or cycles per second in this unit, right? So if I want to know what that wavelength was, remember this is 3 times 10 to the 8, and divide that by 101.1 times 10 to the 6, which is about 1.01 times 10 to the 8, and turns out that the answer is very close to 3. So the wavelength, this lambda, right, of your carrier wave that sends the information you're listening to, the music basically, to your radio, the wavelength is 3 meters. Wow, isn't that interesting? We've got 3, is that right? 3 times 10 to the 8th divided by 101.1 times 10 to the 6th. Yeah, it's like 3 meters. Wow, that's pretty cool. That means that right now, right, I got a radio down here. I know, I'm old school. That's okay. I got radio down here. And if I turn on a radio station here, let's see. Excuse me, when I turn on my radio.
NPR News, this is All Things Considered. I'm Daniel Lester.
And I'm Elsa Chang.
Anyway, that was not 101.1, that was 93.9, but you know what I mean. When that happened, what was going on was that when I turned on the radio, all of the, let me turn the radio off again because we're done with the radio for now. And the radio, when I turned the radio on, what happened was that the equipment inside the radio turned on and basically said, hello, I'm looking for, because I tuned into this whatever radio station it was, right? 93.9. In this case, it could have been 101.1. If I say 101.1, I turn into, and then my machine is like, okay, I'm looking for waves that are exactly that length. It's like 3 meters long that are coming through your room. And then if I see them, I'm going to lock in on them. I'm going to grab them. Then I'm going to use my antenna basically to detect them and then gather them. Once I gather them, it's basically like a telescope, right? It's not like making a picture, but it's gathering the waves. And then inside the radio, it further breaks down the wave, figures out the encoding on the electromagnetic wave, that's 3 meters long, of all the sound that had been recorded in the broadcast studio through the microphone and then sent out after it was coded or multiplexed into the carrier frequency. Pretty cool, right? Yes, it is super cool. It is awesome. The details are a little bit beyond the scope of this class, so I can't go into too much detail about it. I'm sorry, I wish I could, but it's super cool. Anyway, it's electromagnetic radiation. And you know now that right now, throughout, there's 3 meters, 4 meters, 2 meters, a few meters worth of wavelengths of electromagnetic radiation zipping all through your house, all through everything. It's going through your body. Yes. Are you harmed? No. Did you realize that this has been going on your whole life? There's been radio waves going through your body all your life. Have you been injured yet? No, right? So obviously not all radiation is harmful. In fact, that radiation just goes right through walls, right? very easily. In fact, if you have a brick wall over here, but I'm listening to radio over here, I can be right behind the brick wall, but any kind of radio waves that are coming through the brick wall, no problem. It's like the brick isn't even there. Isn't that funny? So some electromagnetic waves, like radio waves, can go right through walls. Other kinds of radio waves, electromagnetic waves, like light, for example, visible light that we can see with our eyes, cannot go through a brick wall, right? Bounces off the brick wall, but it does other things, right? So for example, I can actually see them. I can't see radio waves right now. Radio waves are bouncing on them all the time. I can't see them, right? But I can see visible light. I see you and you see me. All right, if you know that song, let me know. Send me an email. I'll give you a point. Remember, 1,000,000 points, letter grade. Da 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 da. Okay. Anyhow, that might be a song you might hear at 101.1 FM here in this part of the country. That's all the hint you're going to get. Yeah, you got to tell me what song that was. Anyway, electromagnetic radiation, you think about it that way, right? In terms of waves and light and things like that. And then what about the energies of photons? How are they individually energies of photons? And that gets us back to Max Planck. And I will share with you how he kind of deduced mathematically that this should happen. And it has to do with that thermal radiation I was talking about. Remember? Okay, so I'm going to draw for you what the experimental physicists of the 1800s, okay, heading all the way up to about 1900, figured out about how much or where or which way the thermal radiation, the electromagnetic waves, came out of objects that were heated to high temperatures, right? And you looked at their colors and things like that. All right, and this is what happened. I'm going to draw a graph. Okay, this is what they did. They graphed it. And I'm just going to graph it here now. So on the vertical axis of this graph, okay, it's going to be how intense the light is, the intensity of this light. All right. And then on the horizontal axis, I'm going to graph the wavelength of the light. Right, remember how like the electromagnetic waves are like 3 meters long, right? Now the intensity of light varied on the wavelength at different levels, right? But they always, regardless of what wave peak, of what temperature, right, the thermal radiation source would emit its light, it would always have a characteristic shape. Kind of interesting, right? It's a weird shape. It's a shape that when scientists looked at it, they were baffled. What happened was that as the wavelength was shorter, right? Shorter wavelengths are closer to this vertical axis here, and longer wavelengths are heading in this direction. What would happen is you would always, regardless of, you would always have like a sharp increase from short wavelengths up to some sort of a peak. And then you would have a gradual slowing down, going down on the long wavelength side. So for example, you would have say like that, okay? Sharp peak and then a gradual decline as you sort of going sort of wavelengths, right? Here's the intensity and here's the wavelength. And so it was a sharp up to a peak and then it would be gradually declining down this way. Now this was true regardless of what the temperature was. But depending on what color or what temperature it was, the peak would be in a different location. All right. So in other words, if something were glowing green and it happened to have that kind of structure, if something were glowing red, it might have the same structure, a sharp rise and then a gentle slope and going down, just like that same shape. But it would be less intense, right? And the color would be further over and the wavelength would be longer. Now, if it were, say, blue, right, which has a relatively long wavelength, a short wavelength compared to red, what would happen is that you would have a similar thing. You'd have a steep rise and a gradual decline, kind of just like this. But the peak would be a little bit at shorter wavelength still. So something that's glowing blue would have a shorter wavelength peak. Something glowing green might have a medium wavelength peak, and something glowing red would have a longer wavelength peak. You had this variation, but the shape was always the same. And so people are like, what the heck shape is this? They couldn't figure it out, right? Now, the way that astronomy works, the way that physics works, the way that all of this understanding of the universe works, as always, right? Dum, da, da, dum, is with our scientific theory model structure thing, right? What happened was that we noticed facts about electromagnetic radiation, that light is a wave. Okay, good. That was built up from theories past. So then scientists started gathering data to try to figure out what the distribution of intensity as a function of wavelength would be for hot objects. And they came up with this mathematical law, right? See how there's the law. It would have a sharp rise and then a gradual decline. And then the peak location, the peak wavelength, and the intensity would change depending on how hot the object was. The hotter the object was, the shorter the wavelength was where the peak was, and higher the intensity was for the object. So those are laws, right? Those are now mathematically describable laws of nature. But why? Why? Why does it work? And that's why you have a hypothesis. When you have the hypothesis, then you make predictions from it. You say, I believe that these laws are true because this is the nature of light. This is how light works. Okay. And then once you do that, say, well, if light works, and that explains the stuff that we know from before, let us say, let's try to find something that proves or that shows that that's actually true, right? In other words, up here, I'm going to make a prediction. If my hypothesis is correct, okay, then when I see something out in nature that I haven't explained yet, like using this hypothesis and these laws, it'll work, right? If it doesn't work, then it gets falsified, like, oh, well, I'll keep trying until I find a good hypothesis that gets confirmed. But if it gets confirmed, then you get up here, it becomes a scientific theory, which is cool. And then it comes back into this pool, this base of facts, and then you build up all over again. You keep building and increasing, and that's the cycle, the engine of scientific discovery, okay? So here's what Max Planck did. Max Planck came to this hypothesis of explaining this law stuff and basically said, well, if you try to explain this mathematically using the mathematics of waves, it does not succeed, right? It just doesn't quite work because there's nothing in wave theories or mathematical theories of waves that would show you that you have a sharp peak and a rise that's very steep and then a gentle decline. You could have a gentle decline, but then you'd have a gentle increase too. Why do you have this sharp peak? And what Planck explained in his hypothesis was that if the light were added up in terms of little bits of light, pieces of light, right? Instead of waves, you could add up little pieces of light to make a mathematical equation that would fit this very, very well. And that mathematical equation, like I said, is pretty complicated, but it turned out to be correct and it matched everything right. And you had to use this idea that light came in the form of particles as well as waves. It could be one or the other, right? And I was like, wow, mind blown. People were really impressed, but they weren't really quite sure if it was correct, right? The hypothesis came out around 1900. And so it was like, well, okay, it might be true, might work out well, but we have to test it. How do we test its prediction? And what happened was that Albert Einstein, this guy down here, how he said that light must be a particle and a wave, right? He basically took Planck's hypothesis and said, look, I believe Planck's hypothesis explains something else that he had not predicted, something that he had not said it explained. And that was a thing called the photoelectric effect, okay? And I will write that down. We won't talk about it in great detail here, but you should just be aware of its existence because that was the thing that was named on Albert Einstein's Nobel Prize, okay? The photoelectric effect. What happened was that Albert Einstein used basically Max Planck's idea of how much energy each piece of light, each photon should have to explain this long-standing problem in physics called the photoelectric effect. They couldn't figure out why certain systems worked out this way. Albert Einstein said, it's because Max Planck's hypothesis is correct. See how Max Planck's hypothesis shows this is to be true? Pretty amazing, right? it works. And people were like, man, Albert, you are right. This is a prediction that was confirmed with Planck's hypothesis, even though Planck wasn't trying to explain it. Right? See how that goes? So as a result, that was a confirmation, a piece of support, right? If it hadn't worked, let's say if the photoelectric effect showed that Planck's idea was wrong, then Planck would be like, oh well, my hypothesis was falsified. We'll improve on it and see if we can do better next time and get a better hypothesis that can be confirmed. But the photoelectric effect ideas, right, that Albert Einstein did confirmed that Max Planck's idea that each piece of light is basically a certain particle of energy. That was confirmed. And so what is that amount of energy for each particle of light? It turns out, well, its relationship with frequency is direct. The energy of a photon, okay, is equivalent to some number, a conversion factor basically, times its frequency, the same frequency that's up here, okay? Which means that, see, you have, if frequency, right, if you divide both sides by lambda, then you wind up getting F equals lambda over C, or C over lambda, excuse me, divide both sides by lambda, right? Divide both sides by lambda, and you wind up getting C over lambda equals F. So I can substitute here, instead of saying HF, I could just say HC over lambda, right? Now this F over here is part of this sketch, like the frequency, how many waves would pass this point every second. I can figure out what the frequency is. And then here is a little sketch about the wavelength, just to remind you, it's peak to peak of a wavelength, right? Or trough to trough. It's all the way from like starting from one extreme and getting back to the other extreme. That's what a wavelength is. So this conversion factor became known as Planck's constant, right? Mr. Planck, 6.63 times 10 to the minus 34 joules times seconds, which means that if you have a frequency of certain number of hertz or a certain number of cycles per second or waves per second, you multiply that by this number, this tiny little number, 6.63 times 10 to the minus 34, then you get the number of joules that each piece of light holds. That's pretty cool. Just think about it. The E equals HF, right? That means that each piece of light, which is coming at a certain frequency, because remember, it's also a wave, right? Each piece at that frequency has a certain amount of energy. So, for example, that doing that thing in our head again, remember you have the E equals HF, right? If you have the H, 6.63 10 minus 34, and if the F was 101.1, right? 101.1 times 10 to the 6 hertz, that's 101.1 megahertz. Do a quick division, 6.63 times 10 to the minus 34 divided by 101.1 times 10 to the 6, and you wind up with a really small number. It's 6 times 10 to the minus 19. No, it's even smaller than that. 6, well, I'll do it in my head just for fun. 10 to the 8 on the bottom, 10 to the minus 34 on top, HC over lambda, wavelength, frequency, multiplied 6, 101.1, it's 6 roughly, 0.6, all right, times, I'm just did two significant digits here, 6.6 times 10 to the minus 26. Oh man, I just keep doing it in my head. I'm getting all messed up. But anyway, yeah, it's a very, very small amount. It's a 0 point, a lot of zeros after it, and then a 6. So it's really, really small, right? Remember how much a joule is. I'm going to go back to my trusty water bottle here, which I sip from all the time. Refreshing. And notice that, remember I've talked before, if this water bottle is about 1/5 full, right, it's got about 100 grams, and if I lift it 1 meter, or about 39 inches or so, I bring it up that high, that's 1 joule of energy that just landed on my hand. All right, it took 1 joule of energy for me to lift it up, 1 joule of energy to let it drop back down. Wow. So this is like a billionth of a billionth of a billionth of a joule. That's really, really small. Thank goodness, right? Because remember, we were talking about how many of those photons, how many of those waves were coming through the walls at me all the time, right? So if each one of those photons had hit me with any kind of energy at all, I'd be like, it hurt. That would not be cool. But thank goodness the energy is so low and the waves go right through me. And then those little tiny particles, even if they were to hit me and not go through me or whatever, I wouldn't even worry about it. No big deal. It doesn't hurt. I don't feel it. I don't see it. But I get to hear music from it. Da 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 da. Okay. Anyway, it's all good. That's the story of light, right? I will give you another example, just a personal example about the frequency and the energy of light. And then we're going to talk about the whole electromagnetic spectrum. Gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio waves. There is so much good wave stuff to talk about. We might have to wait till the next lecture to get to that part. Oh man, I can't handle that. Tell you what, I'm going to put some into your study guides. You're going to watch a little bit about all those cool electromagnetic radiation regimes. We'll glance over and talk about them a little bit more next time. Okay, but mostly I need you to use that resource, that information to really get you to understand the electromagnetic spectrum, which is super duper cool. Okay, all right, make sure to watch those things. All right, so I'll give you this one more example of how you use these equations because it's fun and because it's useful, right? Remember, for light, c, the speed of light, is the speed of the wave of light equals f lambda. And then meanwhile, the energy of a photon, E equals hf or hc over lambda. Okay, so that's a very, very useful set of equations. Now, one practical example of how that light actually matters to me or to you, but in this case, especially to me, because it had to do with my daughter. My daughter was born 6 weeks premature. So a little preemie baby, 5 pounds or so. No big deal. Turns out she's fine today. She's doing great. Very proud of her. She's awesome. She's healthy and all that. But when she was born, her body, because she was a preemie, was having a hard time dealing with some of the waste products in her body. Okay, they were called bilirubins. Some of you might know about this, but these bilirubins, they made her skin look kind of yellowish, okay, get a little bit of jaundice out of it. And basically the doctors, the neonatologists, they looked at her and said, uh-oh, she seems to have a lot of bilirubins in her body. We can get rid of them. How are you going to do that? Well, you don't want to do surgery or anything like that. It wasn't that serious, but we definitely wanted to get rid of them. Turns out that if you have a certain wavelength of light, and that wavelength of light is to hit the baby's skin, then what happens is that light won't harm the skin, won't give you a sunburn or anything like that, but it's actually like bright blue light, all right? Bright blue light. And that light at that bright blue wavelength, if you happen to shine it on the skin of a person, or in this case, a little tiny premature baby, then what happens is that it causes chemical reactions in the body. The skin, and it will go through the skin and it'll work in the body in such a way to actually help the body break down those bilirubin chemicals and allow them to pass through your body and your system, no problem. So what happened was, for several days and nights, our sweet little baby, our daughter was put into this warm, gentle bassinet in the neonatal unit, right? In the NICU, neonatal intensive care unit. And they put a nice little thing over her eyes so that the bright light would not bother her eyes, right? Because our eyes are sensitive to the light. And then she just in this warm thing, and then she was put in under these lights, big bright fluorescent lights that were shining this bright blue color. And then she was like turned over regularly so that all the different parts of her skin would be exposed to this blue light. And sure enough, all the bilirubin subsided and her yellowish skin turned nice and pink again. So that was lovely. So that was the nature of the bilirubin lights, the Billy lights. And if you want to look it up, you can look up the story about how Billy lights work. This is a really neat technology that they first started to develop. The doctors did, doctors, medicines, medical physicists, right? Physical physicists that work in the medical field. They figured out in the 1980s that you could start shining blue light on people and their bilirubin counts would drop. Pretty cool, right? And so I actually asked the doctor when I found this, because obviously I'm a physicist, astronomer type person, right? I'm like, hey, doc, I asked the neonatologist, what is the wavelength of the bilirubin lights? What's the wavelength of the light that's coming out from the Billy lights? And she was like 4,200 angstroms, maybe? She's like, I'm not exactly sure, but I think it's around 4,200 angstroms. I was like, oh, okay, that makes sense. And so I will tell you, 4,200 angstroms, right? Angstrom is a very, very tiny, small amount. You may remember me talking about an angstrom is approximately the size of a hydrogen atom when we were talking about the Standard Model and atoms and molecules and the Rutherford atom and things like that. It's about 1/10 billionth of a meter. Okay, so it's less than a billionth of an inch. It's about a billionth of an inch. Now, 4,200 angstroms. The term angstroms is usually used by astronomers more often than physicists. Very often physicists will use the term nanometer, which is a billionth of a meter, right? So it turns out that 4,200 angstroms is about 420 nanometers. So I'm going to use that term nanometer because you've heard of that before, nanotechnology, right? There's things that are about a billionth of a meter in size. So it turned out it's 420 nanometers. Now, that's more than 4,000 times the size of a typical hydrogen atom, which is kind of big, right? But on the other hand, 420 billionths of a meter makes it like only 0.4 millionths of a meter. And that makes it 100 times, more than 100 times smaller than the thickness of a typical sheet of paper. Okay, so this is a very, very small wavelength, right? Unlike those radio waves that are like 3 meters long, which is almost 10 feet. These guys are really, really tiny, right? Piece of paper, and then shrink it another 100 times the width of the sheet of paper, and you're just barely seeing the waves of this light coming through. But that's the light that makes that bright blue color that our eyes can sense, which is why our daughter, was wearing those cool little like blocking sunglasses type things. But they were, it was a very interesting time. And so let's go back to that example, which I've written down here. The Billy lights are at 420 nanometers, right? The bilirubin lights. And again, I encourage you to look up Billy lights if you feel like it, but this is just my personal example of lights and knowing how much is going on. And so the speed, right, is again the speed of light, 3 times 10 to the 8 meters per second, and multiplied by the wavelength, which is 420 times 10 to the minus 9 meters, which means that the frequency was 7 times 10 to the 14 hertz. So that's 700 trillion hertz. Remember that the radio was 101.1 megahertz? Well, this is terahertz. So each terahertz, right, is basically a million megahertz. Wow. So you got megahertz, gigahertz, terahertz. So this is 700 trillion hertz, as opposed to that, which was 101.1 million hertz. So this frequency is way higher than that. But that's because the wavelength is way smaller than that, as you might expect, right? And so if you figure out using the Planck formula, right, E equals hf, let me flash that in front of you again to remind you, right? The energy of a photon is Planck's constant times the frequency. So if I do that, the E equals h, right, Planck's constant, times the frequency, which was 7 times 10 to the 14 hertz. And so the answer is 5 times 10 to the minus 19 joules. Remember, the other one was like 10 to the minus 20 something joules. This is 5 times 10 to the minus 19 joules. Oh, it's much bigger, right? It's much bigger. Great. But whether or not it's much bigger or not, it's still 10 to the minus 19 joules, a tiny, tiny little bit. It's less than a billionth of the amount of energy it takes me to take this up here and then drop it. Remember that? Okay, if I take this up here, it drops down there. That's 1 joule. I would need 2 billion of those bilirubin lights, photons, to hit me to get equivalent energy on my body. All right. And of course, obviously, that's not happening anytime soon with me. However, with my daughter, when she was in the NICU, right, that energy was just the right energy to stimulate her cells to break down the bilirubins in her body. Pretty cool, right? So individual light, in this case, was helpful in the medical environment. The other kind of light, electromagnetic radiation, which I can't see, but it's still a kind of light, radio waves, in other words, in the kind of electromagnetic radiation, a kind of light, just not visible light, but light nonetheless, allows me to listen to music. So that's just two examples of how light works in our lives, and that mathematical connection is really powerful and really useful. And I encourage you to learn it because it's kind of nice to know. And not only that, you get to know all the rest of the stuff about light in general. Okay, all right, so we're going to get more about all electromagnetic radiation in the next lecture. Thank you so much for your time. I hope you've been filling out your study guides, as I said before. If you have any questions, of course, feel free to ask. We got people, and we're happy to help. Thank you so much. I'll see you in the next lecture, okay? Thanks. Remember, fill out those study guides. Stay in contact. Keep us posted and stay up to date. Good job. Thanks. Talk to you in the next lecture.